Hi, this is Professor Gutierrez, and we are going to do Chapter 4.3. What are we looking at here? Completeness? Completeness. No, completeness is very different. Complements, we already talked about that. Conditional probabilities, talked about that a little bit. And Bayes' theorem. Again, like Beowulf. You talk about it, you can't remember it, and they make a movie about it with Angelina Jolie that has nothing to do with the actual story. Nothing. Nothing. No. All right. So if we have several trials, at least one specific event, we consider conditional probabilities. Right? Sorry. I'm going all over the place. All right. Provide a brief description of Bayes' theorem. That's what they do. That's what they claim to do anyway. When finding the probability of some event occurring at least once, we should understand the following. At least one has the same meaning of one or more. A complement of at least one is that no events occur. This is the example I showed, where we had 4 and 1. 4 boys? Yeah. All right, finding the probability of getting at least one of some event. Let A be at least one of event. Then A bar is getting none of the event. Now, sometimes you'll also see this as A to the C, and that's just A complement. Probability of A bar is probability that event A does not occur. Subtract the result from 1, boom, at least one event has occurred. Very useful, very often. Let's take a look at this one. Accidental iPad damage as opposed to intentional iPad damage. A study by Square Trade found 6% of damaged iPads were damaged by bags or backpacks. 6%. If 20 damaged iPads are randomly selected, find the probability of getting at least one that was damaged in a bag or backpack. Is the probability high enough so that we can reasonably be sure of getting at least one iPad damaged by a bag or backpack? So 6% are damaged. So the chance that that one isn't damaged by iPad would be, let's see, that would be 0.94. So we simply do 0.94 to the 20 power, 1 minus that, and that will give us a probability of at least one iPad being damaged within the bag or backpack. Well, let's take a look. At least one of the 20 damaged iPads was damaged. Okay. 2. Identify that the event is a complement, not getting at least one iPad damaged in the backpack. All 20 iPads damaged in a way other than bags or backpacks, like hammers or saws, chainsaws. Ooh. All right. Chainsaw backpacks. No. All right. Find the probability of the complement by evaluating P complement. P complement, or P bar, is equal to P of all 20 iPads damaged in another way. So 0.94 to the 20th power, which is 0.29. That means the probability of none of, or at least one of them being damaged is 0.710. Let's go back to that. 0.710. Show a little bit lower than I thought it would be. 0.710. Right. Guess we'll keep going. So we got a group of 20 iPads. That's a 71% probability, or a 71% chance of getting at least one iPad damaged by the backpack. Now, that probably means we will get at least one iPad damaged, but that is not a very high probability. So, I would say probably not the greatest chance. More than half, but not sure. All right. Conditional probabilities, and we talked about a little bit of this. The probability if something has already occurred, A given B. What are the chances of, you being shot if somebody shot you? That's a bad example. Okay. In a minute. Okay. Anyway, notation. Probability that B given A denotes the conditional probability that event B occurred when given that event A has already occurred. So A occurred, so we know A occurred. Now, what are the chances that B will occur? Now, example, World War II, there was an alliance between Poland, France, and the UK, if there was an attack by Germany. And they were called the Big Three to take on Germany. That Big Three thing did not last long, by the way. And so when Germany attacked Poland, you now have what is the probability that the UK and France will declare war on Germany, given that Germany has attacked Poland. Example like that from history. France actually declared war first, and then the UK declared war. All right, conditional probability of B occurring given that A has occurred, assuming event A has occurred. Yeah, we know that. And the formula that we get from the probability of A and B. So probability of B given A is equal to the probability of A and B over the probability of A. Mind you, if we turn that around, the probability of A given B, so if it's probability of A given B, that would equal probability of A and B divided by the probability of B. So probability of A given B is not the same as the probability of B given A. It's two separate things. Pre-employment drug screening. I've heard of those. So, if one of the 555 test subjects, we have 555 test subjects? Oh, we do, yes. Is randomly selected, find the probability that the subject has a positive test result, given that the subject actually uses drugs. That is, find the probability of positive test result, subject uses drugs. Well, the subject uses drugs is 50%, or 50 people are using drugs in this sample. 45 have positive test results. That is, 45 over 50 would be the positive test results given the subject uses drugs. And I do that by doing these two, or this and this divided by this. Right. Subject uses drugs divided by positive test results. $45 over 50.9. We can do it. We can do it. Formal approach is the exact same thing. 45 over 55. Subject uses drugs, 55 over 555. Get the following, divide. We get 0.9. The 555s cancel. Sometimes intuitive approach is better, sometimes the formula is better. It's good to have them both. All right, this is the probability the subject had a positive test result. All right. Okay, here's what we want. Subject uses drugs given a positive test result. So now we're switching it around. We're saying, what are the chances that the person... So instead of P of A and B over B, it's going to be P of A and B over A. Probability of A. It's going to be 4.5 over 70, so that's going to be 0.643. So if you got a positive test result, you probably do drugs, but not a high probability. Nothing I would bet the house on. 0.643. All right. So this is just saying that those two are not the same. So switching them around does not equate. 0.643 is not the same as 0.9. Right. And then this is just confusion of the inverse. Just saying it explicitly, P of B given A is not equal to P of A given B. All right, and sometimes they will be, but usually they are not. All right. Consider these events. It is dark outside. It is midnight. The probability that it is dark outside, given that it is midnight, is probably 1, unless you live in the Arctic or Antarctic. Probability that it is midnight, given that it's dark, is pretty much 0, because midnight is an exact time. So these two are not the same. So that's just an example to keep in mind. All right, Bayes' theorem. What does Bay have to say? Do we trust him? I think we do, because he has a theorem. You can't lie if you have a theorem. We extended the discussion of conditional probabilities to include applications of Bayes' theorem, which we use for revising a probability value based on additional information that is later obtained. So you have an idea of a probability, but as you get more and more information, you can update that probability, and you should update that probability. What are your chances now? What are your chances now? How are you doing now? How are things going now? Oops, did not mean to go up there. Oh, goody, the cancer example, everyone's favorite. Certainly my favorite. Assume cancer has a 1% prevalency rate, meaning that 1% of the population has cancer. Denote the event of having cancer as C. The probability of C is 0.01 for a subject randomly selected from the population. Not randomly selected from an oncology department, because that's much, much higher. All right, the result includes the following performance characteristics of the test of cancer. So the probability of cancer is equal to 0.01. False positive rates are 10%. True positive rates are 80%. And look at that, what this is. The probability of a positive test result given that cancer is not present is 0.1. Probability of a positive test result given that cancer is present is 0.8. Right, we need to write those the right way. The probability that you have cancer given that you have a positive test result. All right, so not that. I'm going to write this over here, and I don't have to do full screen. There we go. Well, let's take a look at some things we got here. And get rid of all that. Let's go. All right. So I go on to something new. The probability that someone has cancer is 0.01. The probability of a positive test result given no cancer is equal to 0.10. And the probability of getting a negative or a positive given that you have cancer is equal to 0.80. So at least it's higher. That's why. So we're going to look at a table. Oops, not there. I think this is enough, but I'm going to go out one more just in case. All right, so how do they do it? So cancer, you can either have a positive or a negative, or you have no cancer. So let's say we have a total of 1,000 people. Then the number of people who have cancer is 0.01 of that, so that would be 10 people have cancer. The number of people who don't is 990. All right, and that's just 10 minus, or 1,000 minus 10. Now the probability of no cancer given a positive test result, so no cancer given a positive test result is 0.1. Or a positive test result given that you have no cancer is 0.1. So that's going to be 99 divided by 990. So that's 10% of them get a positive. Now, of those who get cancer who have it, that is, well, what is 0.8 times 10 is 8. That leaves 2 here, and that leaves whatever the heck is that there. So that's going to be 898. There we go. We get that from the conditional statements. Now they're going to do the same thing. They're going to do more slowly because they're not as awesome as we are. All right. 899 to 891. 891. I knew that. 990. So this is the table that we have. Okay, we can do that. That is good. All right, this is just showing how it's built. Assume we get 1% that have 10. We got 10. The rest are 990. 10% of those. The rest are here. 80% of those. The rest are here. Exactly what I just did. Now, solution to the problem is said to find the probability that you have cancer given that you have a positive test result. It is 8 out of 107. So you still have just a 7% chance of having cancer if you have a positive test result. You might want to talk to your actual doctor about this rather than taking it from a stats class. Because I'm suspecting they probably do like multiple tests just to make sure. They're not going to tell you positive if they don't know for sure. So, false positive, true positive, divide it 7%. So you started out with a 1% chance when you didn't know nothing. And now we got a positive test result, so you know your chances are 7.5%. You also know your life's going to suck, for a while at least, and quite possibly much longer. Based on the data, a positive test result should not be devastating news. It may be wrong, but I would talk to the oncologist, not me. Again. So prior probability, what we knew before, 1% chance. Posterior probability, that means behind you, or your booty. Sometimes people call that booty a posterior. Revising it using additional information. Oh, you got a positive, and I can feel a tumor. Well, that's pretty strong. My mother actually had cancer. She had breast cancer, and she was able to feel the tumor before it was detected on a test. It was very, very rapidly growing tumor. While she was going through chemo, my dad ended up getting cirrhosis of the liver, and then she got a septic infection and went into shock. So, good times. Yeah. Made it through. Lost half a foot, but, you know, she still has 5 toes. So, and my dad's still going around waiting for a liver. If either any of you have a spare, yeah, just, you know, send me a message. I'm assuming you don't. So. But yeah, talk to your oncologist. Don't look at this thing. That just seems bad. Right. Prior probability, 0.01. Posterior probability, 0.07. And then you could have additional posterior probabilities as you gain more and more information. And that is the end of section 3. 20 minutes. Not bad.